morning, everyone. So today I'm going to talk about the case study we've done for large compartments. So first, I'm going to talk about the background, selection of fire model, specifically about GoZone, and then talk about the analysis outcomes and other considerations. Why do we talk about large transport hubs? In conventional design, we would require all steel members to be fire protected, and that'll actually be the convenient but also the lazy way, which is the prescriptive fire rating. But those transport hubs, usually you have a really large compartment, and each area will be quite well defined, unlikely to change over the lifetime of the building. And by having each area well defined, that also means the field distribution is well defined. And this is the situation when performance-based design can be really beneficial to the project. And before we go into further about the performance-based design, we need to have the common understanding with all the stakeholders. And these actually, running simulation, of course, takes time, but then establishing this background is very important before we can even do anything else. I'm sure people are aware of the Cardington fire test, what the floor look like. Unfortunately, not many people outside of this industry understand, and we have to explain that to many stakeholders several times. Life safety is not really an issue here when we talk about structural fire assessment. Of course, we care about life safety, but the time when we have to worry about life safety and the time when we may have the structure deformation, they are at the different stage of fire. So we shouldn't mix those together. And reduction of fire safety system, for example, fire alarm system or the sprinkler system, those have nothing to do with structural performance-based structure fire engineering, because we are not here to propose changing of the sprinkler system or fire alarm system. And we are not looking at evacuating people from deformed floor. Again, that's to do with different time in the in different stage of fire. The background here, for this building, we are looking to the ground floor area, which has the conveyor area, baggage storage hall. Above that, there's the retail, food hall, circulation. For this building it also has the sprinkler system, which influence how we define the input fire. It also has smoke detection, smoke extraction. That doesn't really affect the fire growth that much, but that's adding the sense of safety for people, consider about the life, the occupants' life safety. And there's dedicated firefighting crew on site. We are not relying on that in terms of in terms of the structure fire design, but that's also good to know for all the stakeholders. And here's the advertisement part. Why do we use SAFIR? The reason we use SAFIR is it is simple. It is easy to understand what the program can do and what it cannot do. Everything is basically well established, and people can find information online. Similarly, straightforward to explain to peer reviewers and local authorities what we have done. In terms of what the program cannot do, we all know is finite element analysis. It doesn't really handle the shear situation that well. But that is something, as long as we explain to all the stakeholder, usually that can be addressed in the acceptance criteria, that part, instead of causing problem later on. But there are a lot of simple calculation method out there. Why do we use SAFIR? And another point we have to make is it is sophisticated. With SAFIR, we can include the decay phase and cooling phase of the fire, and we can consider the fire spread and traveling fire. So the fire doesn't need to be always about the entire compartment. And you can look into the radiation from the fire to different structure elements. And it does work with various materials and different dimensions of members and no limitation on the compartment shape. It's probably easy to say, but a lot of other programs, they have those limitations, and then they, even though they are simple to use, but the outcome may not be too useful for as a designer. And the next thing is the selection of fire model for this project. For a large compartment, and talking about fire spread or traveling fire, we can use FDS, which is the large ED simulation technique for turbulent fluid motion. And everyone, well, most people would know FDS is useful to give you the temperature, the chemical species yield, layer height. All of those information will be given in the output file. And the good thing about FDS is we all know it is validated for compartment fire, and you can build different compartment shape. So, basically, you don't have to explain that to people. Most people can understand this part, and most people understand it is time consuming. Originally, I was thinking, well, it's slow, but if it's talking about whether it's fast or slow, that's to do with your computer. The reason for saying it's time consuming is, well, even if your computer is very fast, because it's trying to give you all the other information, then it does have to take time to do all those calculations. And in terms of fire spread, that is something important for large compartment. You have to, well, the simplest way is you define the fire spread speed. But then, well, is that really scientific? Then that's another thing you have to justify. And if you have to define fire spread speed by yourself, then let's move on to the next fire model we can look at. That's SAFIR for SAFIR, which was part of the European research project SAFIR. I mean, well, Professor Jean-Marc Vincent and then Dr. Marion Charrier, they were part of this group looking at the SAFIR project. And SAFIR for SAFIR was developed based on SAFIR tests. And the focus was on fire spread. That program, you can use that to define, you can use the defined fire spread speed. And then it becomes quite an easy program to use to look into how fire go across the compartment. The compartment needs to be rectangle or square. So if I only want to look into something that's for structural fire analysis purpose, SAFIR for SAFIR probably is, and if the compartment is rectangular or square, SAFIR for SAFIR will be, well, more ideal to use than FDS, because it will also give me the result very, very quickly rather than waiting for the simulation to run. Then the next thing is GoZone, which I mean, you can read here. It's about the cellular automata framework coupled with the zone model, and it is fast to execute. The downside is there is no friendly user interface yet, but we are going to talk more about GoZone in the next few slides. So it's developed by the University of Liège, by Dr. Antonio Gamba, and also supervised by Professor Jean-Marc Vincent. You can find more detail from that reference. The compartment is discretized using GMSH, which is the open source program. You can also download online. The good thing about GoZone is the compartment side. The compartment can be irregular. The shape can be any shape you want. So that's why there's I'm showing a disk here. It can assign different fuel load distribution. So it doesn't need to have the same fuel load across the entire compartment. You can have part of compartment with high fuel load, part of the compartment has no fuel load. And it does consider the compartment boundary condition, for example, the window opening and the wall material, and the density, conductivity, specific heat of the ceiling, floor, and wall material. And if you need to consider window breakage for extra oxygen, you can do that as well. And after discretization, each cell, we call that field cell, you can have the field defined by the growth rate, heat release rate per unit area, the field load in each cell expressed in the way of per square meter, and the height of the base of the field load above the floor level. The calculation considers fire spread through cumulative heat flux and critical energy. So you don't define the speed of fire spread. It's going to do the calculation for you. And you just need to tell the program what would be the critical energy for the neighboring field to ignite. And that is a major advantage of this, because, well, at least it is something scientific rather than you just pick a number about the fire spread speed. And the radiation is coming from the smoke layer to the neighboring fuel cell, or from the fire, which you have to consider flame height. And to consider flame height, you can't just use if you are going to use Hess-Kestad equation, you cannot just use the fuel cell area. If you chuck that into equation, it's going to the flame height, the flame length, flame height is not going to be realistic, which is why there's the modified equation being used in the program. And the program, of course, has been validated. So I'm just here conveying the information, but all of this has been presented in other in other platform. And the GoZone, it can transition from field control, ventilation controlled, just like what you normally can do with the zone model. And it will grow based on the available oxygen. So from here, you can see from the left-hand side with when the fire is starting from the center and then start to spread across the compartment. And it will also tell you which area has become ventilation control burning and which area has the fuel already been consumed. From there, you can generate transfer file and put that into SAFIR. Transfer file, the idea is the same as coupling FDS to SAFIR. What you need is you will need the most important part is the radiance, which is the emitting heat flux in the heat flux energy in the space, and it will be conveyed into SAFIR about how those heat flux affect each structure element in the space. In this case study, the compartment of interest is 7.5 meter high. The overall compartment is 5,500 square meters, which is a large compartment. The storage area is only at the center, 1,380 square meter. Before we run the simulation, we have to come up with some idea about what would be the most likely outcome, and then we protect those steel members. And in this case, we are proposing to protect the members between the columns. The columns are concrete filled CHS, and those have inherent fire resistance. In the storage area, the storage height is 6.4 meter, and under the New Zealand design environment, that's what the authority would like to see is 800 megajoules per square meter per meter of storage area, and this will be it will give you some extremely high fuel load. In this case, you have 5,120 megajoules per square meter. That kind of fuel load And it may sound ridiculous, but that's what we have to work with. And we are considering the uncontrolled fire within the one sprinkler head spray zone, which means the one sprinkler head does not work. And we also have to consider the fuel being available to burn outside the fire, but it has been wet by the working sprinkler. The acceptance criteria we define is no runway failure. The floor will not just collapse. And one way to do that, other than from having no simulation failure, is to check the rebar strength and deflection rate. And of course, we don't want the collapse of structure. In this case, there's also the imposed limit on the deflection, which we define that as 20% of the span length. And you can see the model being built at the right-hand side. And then the fire, the heating up of the structure element, fire at the center, and then the mid-bay deflection is around 400 millimeter. There is not much recovery of deflection after during the cooling phase, but there's no runway failure and there's no collapse. We have done some further check requested by the local fire service about heat release rate per unit area. So we have they want to know whether it's sensitive to the type of fuel load we have in there. So we've tried 1,500, 2,000, and 2,350, which is one of the upper bound in the verification method here. And it shows that the results are not sensitive to the heat release rate per unit area. Also, the fire service, they want to know about what would happen if our starting point of fire is at the corner or at the center. The result I presented earlier, that's having the fire starting from the center of the storage area. And if the fire starts from the corner, then in this case, it didn't really cause a lot of difference. So the conclusions from the case study is, the application of GoZone and SAFIR to predict fire spread in large compartment and potential structural fire response, it does work. And then we can use this for the design purpose. And building with large compartment defined fuel load, they are ideal for performance-based structural fire design. Another thing to talk about here is GoZone is fast to use and can handle various fuel load, fuel type, and irregular floor plate. It gives us effective information. The reason for saying that is for structural fire analysis, we don't really want to know about the species yield or visibility. The important part for us is the temperature and the radiation intensity, and that's the information we can get from GoZone. You can also get that from SAFIR for SAFIR. The downside, the reason why we didn't use that was the compartment shape is irregular. In combination with SAFIR, it is ideal for structural fire design with concrete and steel structures. The reason why we have to emphasize concrete and steel is for timber, because you may have the ceiling burning as well. And for zone model, it doesn't. It's probably not a good combination to have fire from both top of the compartment and bottom of the compartment burning at the same time. In another part of this project, we actually have the CLT sitting on steel frame, and for that part of the project, we cannot use. We didn't use GoZone, and we were using some test results because, what I said earlier, having fire burning from two sides, up and down, that they are not. It is not ideal for using zone model. And the fires. And another thing about CLT and steel frame is, well, we don't really have a good idea about how to rely on the CLT for load transfer. And in this case, we have to ignore the benefit or the use or how the CLT can pass load between the steel members. And then and also in terms of the composite action, we do not understand that very well. So for this model, we have to basically ignore CLT altogether. And that's actually the end of my presentation. Happy to answer questions now.